All right, today we're going to talk about how to draw Lewis structures. I really recommend using something you have around your house as electrons, like Cheerios or chocolate chips, or even better, because it will help you a lot rather than just doing paper pencil. So let's take N2O for example. The first thing you'll always want to do is count up your total number of valence electrons. So I pull out my periodic table. Hopefully you've already written the number of valence electrons based on the column or group that are on the periodic table. So this first group, all of these have 1 valence electrons, 2. We skip the transition metals, 3, 4, 5, 6, 7, 8. So based on that, if I'm looking at total valence electrons for N2O, nitrogen over here, each nitrogen has 5. So I'm going to write nitrogen with 5, but there's 2 nitrogens in the formula. And then each oxygen has 6. And there's only 1 oxygen in the formula. So the first thing I have to do is count up my total number of valence electrons. So 10 plus 6 would be 16 total valence electrons for this compound. So let me count out 16 Cheerios here. 2, 4, 6, 8, 10, 12, 14, 16. And now that I've counted those out, that total number cannot change. I'm going to keep those 16 and I'm just going to rearrange them when I'm drawing my molecule. So to draw the kind of basic skeletal structure of my molecule, you put whatever element is listed first in the middle. The only exception is hydrogen. It will never be in the middle. And then I write the other elements on the outside. So there's another nitrogen and there's another oxygen. And then it's a matter of just rearranging these electrons to first form a bond between 2 elements. And then if I start running out of room, I can put them on outer elements. At first, it's just kind of literally a guess and check. Until you do a lot of these, you're just kind of playing around to seeing what works, because your ultimate goal is to obey the octet rule, which each atom. So the way I've arranged them so far is, it's not correct yet, but we're getting there. Let me check the octet rule. For oxygen right here, this oxygen has a lone pair, a lone pair, and a lone pair. And then it has a single bond, which is made up of 2 electrons, with this other nitrogen here. So if I look at just this oxygen and cover up everything else, the oxygen, quote, feels like it has 8 electrons. So it is obeying the octet rule. It is happy, if you will, though atoms can't really be happy. And then if I look at this nitrogen over here and ignore everything else, that nitrogen also has 3 lone pairs and a single bond. It is obeying the octet rule. It feels happy, if you will. But this poor nitrogen in the middle has only a single bond and a single bond. So if I cover up everything else, except for electrons in its vicinity, it only feels like it has 4. So it is not obeying the octet rule, and therefore it needs more electrons. Now one solution might be to move these over here. Let's say I took and move those electrons over there. If I look at that central nitrogen, now it's happy. Now it feels like it has 8. But now I've messed up this oxygen over here, and that oxygen over there only feels like it has 4. Well, that didn't work. So moving them back and forth isn't going to solve my problem. So instead, I can move them to the middle here, and they can be shared electrons. So part of this covalent bond right here, these shared electrons. And I'm going to do the same thing over here. And now this is correct, and let me check why it is. So let me start over here, check this nitrogen. There are 2, 4, 6, 8 electrons on that nitrogen. Great. On the middle nitrogen, there are 2, 4, 6, 8. Great. And on the far oxygen, there are 2, 4, 6, 8. Wonderful. So they all feel like they have 8 electrons, but notice I have not changed that total number of 16 that I had earlier. So if I want to draw this, then I would draw my double bond to the other end. That was this right here. 2 electrons, 2 electrons. And then here's a lone pair, and here's a lone pair. And it doesn't matter if I drew that over here or I could draw it down here. And then over here, another double bond to this oxygen. And then here's a lone pair, and then again, wherever, it doesn't really matter where I draw it like there. So that's the final Lewis structure for N2O. So let's do one more. Let's try NO2 minus, which is the nitrite ion. Let's count our valence electrons first. So nitrogen, just like in the last one, had 5. And then oxygen, just like before, had 6 each, but there are 2 of them. And then this minus up here, remember that's really a -1. That means an extra electron has been added. So the 1 minus, you're adding another electron. So my total isn't just 12 plus 5, 17. My total is actually 18 valence electrons because of that -1 right there. So count out my 18 electrons. So I counted these. There's 18 electrons right there. Put my first element in the middle and my other 2 on the outside. And then I'm starting to rearrange. Now last time we started off with something that looked like this. So we kind of put 6 electrons or 3 lone pairs around that oxygen. Then we put a single bond, we put a single bond, and then we put 3 more lone pairs. But last time we only had 16 valence electrons. And this one has 18, because again, it's not N2O, now it's NO2. So I've got 2 extra electrons. So the most logical place to put those would be on the central atom here. And if we do our check like we did last time, let's see if we're obeying the octet rule. So if I check this far oxygen atom, it does have 8. It feels like it has 8. 6 of those are actual lone pairs owned by oxygen, if you will. And then 2 of them are shared with the nitrogen, but that's okay. Even if they're shared, it feels like they belong to that oxygen. If I check the other oxygen over here, it also is fine. It obeys the octet rule, 2, 4, 6, and then the last 2 are shared, so that's 8. But this middle nitrogen doesn't obey the octet rule. It only feels like it has 6. 4 of them are shared, and then 2 of them are up there. So in order to then make this nitrogen happy, last time we tried to bring these over here, but we realized it would be depleting this oxygen. So instead, to make them both happy, we'll bring them in the middle and create a double bond. So now let's double check. This oxygen still feels like it has 8, so that's great. 2, 4, 6, 8. The nitrogen in the middle feels like it has 8. 2, 4, 6, 8. And then the oxygen on the right feels like it has 8. 2, 4, 6, 8. So we've stuck with our 18 valence electrons. We didn't touch that number of Cheerios. And every atom feels like it has 8. Remember, there are exceptions. The only one we really care about in our class is hydrogen. So your book talks more about that. But most of the Lewis structures we will do will definitely follow the octet rule. And so if I want to draw this, I would draw a double bond over here to this oxygen with the 2 lone pairs. And now there is a lone pair right here on the middle atom, a single bond to this last oxygen. Notice we could also draw it with these here and these here, and watch how that changes this. This is still a valid Lewis structure. It just moved the single and double bond. Let me show you how that works. Single bond to this nitrogen, and now double bond to this outer oxygen. They both have 18 valence electrons, and they both have every atom obeying the octet rule. So either one is completely valid. It's a concept called resonance we won't get into too much, but both of them are valid. Okay, now let's go to chapter 10. We've learned Lewis structures, and now we're going to figure out the shape of a molecule. So the whole point of drawing a Lewis structure is to eventually figure out what the shape of a molecule is, because the shape of a molecule really influences its behavior. So let's take our example we did before, N2O, dinitrogen monoxide. Extremely important that you draw the correct Lewis structure first, so make sure that Lewis structure is correct. And then to find the shape, the first thing we're going to do is focus on the central atom and count the number of electron groups around that atom. So we're going to define one electron group is either a lone pair, so 2 dots, a single bond, a double bond, or a triple bond. So we're calling it an electron group. Some books and websites call them electron domains. And the reason why we care what a group is that two electron groups are going to repel each other because they're both like charges. So in our case of N2O, we've got an electron group over here, just one of them, and we've got an electron group over here, another one. So in this case, there's only two electron groups. So they're going to repel each other as far apart as possible at a 180-degree angle. As far apart as possible, 180 degrees. If we look at our other example, our NO2 minus, in this situation, around the central atom, we actually have three electron groups. We have a single bond, a double bond, and a lone pair. So if we have three groups of electrons, now when they repel each other, my picture doesn't show it very well. My picture looks like they're 180, but actually, to draw this better, they would repel each other like this. Let's picture the lone pair as just kind of a bubble up here. And then here's my other oxygen, and here's my double bonded oxygen. And they repel each other to be 120 degrees in their bond angle right here. So bringing that lone pair in pushed these two groups down, again, because electrons repel each other. So we needed to define what an electron group was, first of all. And then, based on just simply the number of electron groups around a central atom, that will determine the electron geometry. Notice that word electron is underlined. It's very important. If there are just two electron groups, they're 180 degrees apart, we're going to call it linear. If there are three, we're going to call it trigonal planar, and they're 120 degrees apart. And if there are four groups, we're going to call it tetrahedral, and that's 109.5 degrees apart. So let's look back at our example again. Our first example, we said there's two electron groups here. They're 180 degrees apart, and therefore the electron geometry is just called linear. In this example, we said there are three electron groups. They're 120 degrees apart, and we call that trigonal planar. And if there were four electron groups, we would call it tetrahedral. So then the last piece of the puzzle is, well, then what's the actual molecular shape? Because we've just been using the word electron geometry so far. So molecular shapes, your book uses the word molecular geometries. I like to say molecular shapes so as you don't get confused with electron geometries, but you can say molecular geometries as long as you note this word right here, the actual shape or molecule of the shape or geometry of the molecule. So those are first based on the actual electron geometry, so one of these, but then the number of lone pairs around the central atom matters. And here's where you're going to look in your book, table 10.1. So table 10.1, notice here, the number of electron groups influences the electron geometry. So when there's just two electron groups, the electron geometry is linear. When there's three electron groups, the electron geometry is trigonal planar. When there's four electron groups, the electron geometry is tetrahedral. But there are kind of subcategories. So you're thinking, well, why are there two that say three and three that say four electron groups? And that's because based on the number of lone pairs, it will influence the actual shape of the molecule. So let's look at some examples. So if we look at something that is two electron groups and linear, that's straight across. The word linear makes sense, right? 180 degrees. If we then, though, have three electron groups, the number of lone pairs around the central atom matters in determining its molecular shape. So let's see here. This table helps us show that we could have three electron groups. If there are no lone pairs, that means there are three bonds, 1, 2, 3, no lone pairs. We're still going to call the shape of the molecule trigonal planar. But if we have a molecule that still has three groups, But now one of those groups is just a lone pair, which is actually really hard for us to see. Electrons are hard to see, but they're there. We know that they're there because they've pushed these bond angles down. That is where we have 2 bonds and 1 lone pair right here. The electron geometry is still trigonal planar, but now the shape of the molecule we're going to call bent, because that's literally what the atoms look like. And the reason why this is a whole different word sometimes is because when we look at the molecule shape, we care about just where the atoms are. We can't really see a lone pair, we just infer that it's there. So this is called bent. And then we can look at tetrahedral and figure out where we might have variances based on the number of lone pairs around the central atom. So let me show you just tetrahedral with no lone pairs. So I'm going to have 4 atoms around the central atom. So that would be this scenario right here. 4 electron groups, all 4 bonds, no lone pairs. We're going to keep the name of the molecule the same. But in the next scenario, I'm going to only have 3 bonding groups, 1, 2, 3. And 1 lone pair. Again, that's here. We're inferring it's there, even though we can't see it. We're inferring it's there because our Lewis structure says it's there. I'm going to call the name of this shape Trigonal Pyramidal because it's like a pyramid with a triangle base. And finally, if I have a tetrahedral geometry, because I have 4 electron groups, those 2 go together. But of those 4 groups, 2 are lone pairs. So picture them like Mickey Mouse here. 1, 2, and 2 are bonds, 1, 2. Then I'm going to call the name of this shape bent, kind of like it was up here. The only difference in this bent is the bond angle is 109.5, where up there with the 3 electron groups, the bond angle was 120, a little bit further apart. So that should give you an idea of electron geometry versus molecular geometry based on a correctly drawn Lewis structure.